Ah. Welcome, everyone. My name is Peter Corliss, Technical Marketing Manager at ScyllaDB. I'll be your moderator for today's webinar, Building Event Streaming Architectures on Scylla and Confluent with Kafka. Scylla is a big, fast, NoSQL distributed database that is a perfect complement for Apache Kafka, the big, fast distributed data streaming system, and particularly the Confluent platform, the industry's leading solution provider for your data in motion. Next slide, please. Without any further ado, I have the pleasure of introducing to you our speakers today. Tim Berglund is a Senior Director of Developer Advocacy for Confluent and one of the most recognizable voices in the industry. Mahidar Guntoru is ScyllaDB's Director of Technical Alliances. As well, we have two speakers from the French marketing technology provider Numberly. We are so glad to once again introduce Alexys Jacob, CTO at Numberly. And with him today is Othmane El Metioui, Numberly's Chief Data Officer. Next slide. This is today's agenda. We'll begin with Mahi, who will give a brief introduction to Scylla. After that, we'll hear from our friends at Numberly about how they use Scylla and Kafka in production today. Then we'll return to Mahi to talk about how we've implemented change data capture, CDC, in Scylla. Finally, Tim will show you how to integrate Scylla's CDC feature with Apache Kafka. That's a lot of ground to cover, so let's get right into it. Take it away, Mahi.
Hey, thanks, Peter. I'm going to spend a couple of minutes giving a brief overview about ScyllaDB. We are the company that reimagined the NoSQL database. We have done that by coming up with an innovative close to the hardware design written from scratch in C++. Scylla is API compatible with Cassandra and DynamoDB, but with 10 times the performance and predictable low tail latencies. Our product is open source first, but we also offer enterprise and DBaaS options. Scylla comes from the same folks who developed the KVM hypervisor, which is used by many companies and many public cloud providers. Next slide. Scylla grows with your business as your data needs increase. Our limits are much higher and far exceed other NoSQL databases. Scylla can deliver very high throughput and handle petabytes of data. We're able to support use cases which require millions of ops per second with very low latencies, usually in the single-digit milliseconds. Scylla is an eventually consistent system, which means we provide tunable consistency. I would encourage the folks who are not familiar with tunable consistency to review the CAP theorem. Scylla can scale up as well as scale out. That is, the cluster can efficiently grow both vertically and horizontally as needed for various use cases. We can replicate across any number of data centers and geographical regions, delivering high availability and resilience. Scylla's implementation allows it to support wide columns and partitions. Oftentimes, this is useful for customers who want to migrate from DynamoDB and even Cassandra. Next slide. For these reasons and more, so many companies across many verticals are choosing to go with Scylla. And as a nice side benefit, customers save a lot, as our TCO is much lower than any other NoSQL database. These are just a few of our marquee customers and a subset of the industries we serve. Next slide. Scylla offers a variety of deployment options. You can run Scylla in your data center, on your own hardware, or on any public cloud providers, and even on AWS Outposts. In fact, Scylla is the only certified NoSQL database that runs on Outposts. Scylla Cloud is a fully managed DBaaS solution that is available on AWS, GCP, and soon in Azure. We also provide a fully supported Kubernetes operator. And now we'll have our friends from Numberly speak about how they use Scylla and the Confluent operator. Next slide.
Thank you.
Alexys, over to you.
Hello. Hello, everyone. I'm very pleased to be with you today to share about how we combine the powers of Scylla and Kafka at Numberly. I will be introducing you to our current architecture and explain the components we use in both technologies before letting my colleague Othmane dive into detailed use cases. Next slide, please. At Numberly, we run both Scylla and Confluent Kafka on-premise on bare metal machines. This means that this is our own hardware, network, and automation at play. The key thing here to remember is that we run both technologies on an active-active multi-data center topology because they are mission critical to us. Next slide, please. And running on premise does not mean we are hermetic to cloud deployments. We actually have an hybrid approach with direct connections between our data center backbones and some cloud providers, such as AWS. Running your own multi-data center infrastructure, though, requires skills and dedication that many would better spend in their products. We can afford it after more than 20 years of experience and know-how, but I find it important to say that you have to know where to spend your own energy. Both Scylla and Confluent have high quality cloud offerings, providing a robust response to your technology needs. It's not always the case on our own experience with cloud providers, often lagging behind versions and offering poor observability, especially on highly optimized technologies such as Scylla and Kafka. So when choosing who's going to run and operate your Scylla and Kafka in the cloud, my standpoint is to trust the people behind the technology because they know better and their interest is always aligned with yours. This is especially important when things go wrong, and they will someday, believe me. Next slide, please. So now let's see the Scylla and Confluent Kafka components that we use at Numberly and why in the next slide. On the Scylla side, we have what I think should be a standard for anyone serious about his Scylla deployment, using Scylla Manager and the Scylla monitoring stack. One thing that I want to highlight is that we do use data expiration a lot, and almost on all our data stored in Scylla at Numberly. TTL expiration is very important and powerful to deal with legal data retention constraints, especially in Europe. On the Confluent Kafka side, we use Kafka Connect, Streams, and KSQL supervised through a schema registry and a homemade control center interface and Grafana dashboards. When we started combining Scylla and Kafka, a powerful CDC as the one of today was not available. So we wrote Kafka streams and Python pipelines to synchronize Scylla tables and Kafka topic. Mostly, we were monitoring also the Scylla CDC advancement with anticipation of joy. On the next slide, please. Because now that Scylla has a certified Confluent CDC, we'll be evaluating which pipelines and streams could be replaced with it when appropriate. We anticipate that this will greatly help us simplify our topology. Othmane will give you more details about this by explaining two production use cases that we operate at Numberly, while detailing the limitations that we faced and how we got over them by combining Scylla and Kafka powers. Next slide, please. So hello, Othmane. Could you please take us over and explain how and why we're using Scylla as a low latency remote state store for Kafka stream and pipelines?
Sure, Alexis. Thank you. Next slide, please. All right, let's deep dive. The first use case is about one of our core pipelines to feed real-time behavioral data to downstream business processes. Next slide, please. In this slide, I will describe how this pipeline used to be. As user navigates through websites, our tracking data flowed through our tracking API, which was then queued locally in the beanstalk and then shipped into the RabbitMQ exchange. From there, we had Python programs that had two main purposes. The first purpose of the program was to consume RabbitMQ to build ID matching tables and then save them into ScyllaDB using the right model. The second purpose was to enrich tracking data coming in by using ID matching table that was built previously and then push them to Flume so downstream business processes could benefit from it. This process was used for 4 years until we decided to test out a new solution to simplify our pipelines and reduce latency. Next slide, please. So to reduce latency and simplify the pipeline, we decided to replace our web front end local queuing system from Beanstalk to Redis to improve performance. Then we integrated Kafka to log our incoming events and to build our ID matching tables. These ID matching tables were then synced to Kafka as compact topic in a compact topic using connector. Lastly, the Kafka Stream application was in charge of matching and enriching incoming events using KStream and Ktable join. Just keep in mind that all our applications were and are still running on Kubernetes without any persistent storage. Next slide. What I just presented worked like a charm on our staging platform, but as soon as we moved to production, we faced some limitations on Kafka streams. The first limitation was that retention for ID matching tables that was long, that generated state stores from 150 gigabytes to 1.2 terabytes. We also had to perform successive joins on the different tables, resulting to huge state store inside our applications. Since we're running on Kubernetes, we faced some out of memory issues and our application kept restarting and lost their states. Rebuilding our state after an application crash was a nightmare and costly too, due to user standby replicas. So at this stage, we realized we had to change our approach, as it was clear to the team that the issue was the state store. So going back to the original need, we needed a high available database with low latency read writes and a key value store. So naturally, we looked at Scylla to do so. Next slide, please. So to change our initial approach, what I just presented, today we do not sync matching tables to Kafka anymore. Instead, joining between Ktable and Kstream is replaced with optimized SQL prepared statement to look up data and enrich our pipeline from Scylla. And finally, the ID matching tables are now exclusively hosted in Scylla. Next slide, please. What are the takeaways from this use case? Metrics, and I say metrics, 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 because without metrics, there is no successful tuning. Another takeaway is use Prometheus client. They have a bunch of projects that will help and ease your monitoring. Tuning. Tuning is important in such a pipeline. Size the number of partitions regarding your query. That's important. Mind your time to recovery. You should be able to have at least 3 times the average of your throughput. Add query caching, but no more than your query time execution to maximize your consistency. And of course, make sure to use shard-aware client for Scylla. Next slide, please. Second use case. Here we'll dig into Scylla award-winning for most innovative use case, Synapse. Next slide, please. So what is Synapse? Synapse is our core marketing segmentation engine leveraging Kafka and Scylla. In brief, we gather different data flows that are resourced in Kafka. We then use a set of Synapse microservices to be able to apply business rules while data is moving. Whenever data matches a business rule, the information is persisted in Scylla with a mandatory TTL, of course for GDPR, and also to ensure that if there is no update, the data is deleted and the individual is removed from the segment. Automatically, of course. On our first iteration, we tried a workaround on an existing connector. At that time, results were not as expected, so we rolled back to a custom microservice to sync from Kafka to Scylla. With the brand new certified connector now available, we'll give it a second look. Second usage is distribution. Whenever a sync with an external platform is triggered by business, sign-up services consume segment from the data from Scylla and make it available in a Kafka topic. Next slide, please. While looking at the use case I previously explained, we can see that Kafka and Scylla are complementary to one another, and here's why. Here's why we choose Scylla over native Kafka. We choose Scylla since we have a large number of tables, which will impact our number of topics if we had to use Kafka natively, which end up with 10,000 more compacted topic to be created. TTL management. On Kafka, compacted table adds custom processing logic and complexity, and also propagating Scylla expired data still adds complexity. So of course, we create for expiration event in CDC, which is an open issue, and we're really waiting for it. Leverage Scylla, low latency, and capability to consume and enrich data at scale. But of course, no technology is perfect. So we ended up with some limitations using Scylla. We had some OLAP processing inside this platform that had to perform some counting on high cardinality data. So of course, we started looking at Scylla to do so. So let me explain a little bit the issue. When you have a user, here our partition key on Scylla is part of multiple segments, cluster key. Counting is okay. We can do it through Scylla. A segment, which is still our partition key here, when it has a large, huge number of user, cluster key, this gives us large partitions. And those large partitions bring the counting being a little bit hard on Scylla. So we ended up using Kafka streams to compute those statistics on the fly. Next slide, please. So what are the takeaways of this use case? First, define your model, your table models in Scylla to suit your queries. This is really important. Forecast your data volume on your models. Does it suit your volume? Does it suit your use case? Will it work on production? It is important before going live. Mind large partitions on Scylla, because this can and will damage your cluster if you don't. Kafka streams turns out really great for on-fly aggregations. And those aggregations, an advice should be persisted on an external store to give you the ability to go and do multiple time spans lookup. Interactive queries on Kafka streams are great, but just for real-time hot data. Back to you, Mahi.
Right. Let's go to the next slide. All right. So in this section, I'm going to spend a little bit of time explaining what CDC is, and then we can dive a little bit deeper. Let's go to the next slide. CDC, or change data capture, allows you to query the history of changes made to the database. While querying your database gives you a very static view into your data, with CDC, you get more of a temporal view into your data. It is a log of all the modifications as they happen to your data in the database. Once you enable CDC, Scylla will start capturing the changes to your data, and you will be able to access them asynchronously and do whatever you want with them. Let's go to the next slide. Now let's try to understand some use cases where CDC can be used. Any application which requires a group of microservices to work in tandem with each other, where the state needs to be propagated from one service to another, CDC can be useful there. Some examples here are applications based on IoT, like smart automations, or in retail, like point of sales and inventory-based applications. So just to name a few. If you're an ETL developer, you know how new data arrives in your landing zones, and you have to run a series of data pipelines to transform your data. Now with CDC, your life becomes much easier as we present the new data along with the change log, which provides the necessary data lineage for your application. With CDC, you can also enable various integrations. If your application needs search, now you can stream the data incrementally to Elasticsearch. Or if you need to migrate or mirror your data from one database to another, or if you need to periodically populate your long-term storage like Hadoop or Snowflake or Redshift, then you can stream the state incrementally to these destinations, oftentimes via Kafka. Kafka is a very integral part of our CDC offering. Tim is going to speak a bit more about this in the next part of the presentation. Let's go to the next slide. Now let's take a peek into how it is implemented in Scylla. The features can be enabled by a table, which then creates a CDC log table underneath. That is co-located with the base table. The rows are ordered by timestamp and the modification order ID. Columns are mirrored from the original base table, and each row is mirrored for the pre, post, and delta images. Every record contains the modifications and the TTLs of the data being written. The default TTL of the CDC data is around 24 hours, but this is configurable. This is mainly to reduce a risk of uncontrolled buildup and prevent any overflow. Let's go to the next slide. When you normally write into a Scylla table, the client sends CQL to the coordinator node, which processes it, and then RPC calls are made to the replica nodes. Writing to a CDC-enabled table is pretty much the same thing, but the requests get intercepted and pre-processed at the coordinator, and we optionally issue pre-image reads to get data for pre, post, or image generation. Then the CDC mechanism will piggyback the writes to the log table to the original mutations, which are going to the same replica nodes. So we don't generate more writes, but we do generate more data. This is important to understand. We don't generate more writes, but we do generate more data. So the payloads increase, and we have to size appropriately to account for the additional CDC-enabled tables. Let's go to the next slide. Every mutation sent to a CDC-enabled table generates one or more rows in the CDC log table. There are certain key elements to these CDC log tables, such as you can have pre-image data, which represents the state of the row as it was before the change. You can have access to the row keys, and then the changes to the non-key columns that we call delta, sort of a very obvious name, and also a post image, which is the state of the row after the change were to be applied. Also, every CDC log writes using the same consistency level as the base table. So you get the same guarantees as the base table. Next slide. The CDC log is read through normal CQL statements, which is quite cool, as now you can access a whole bunch of information via CQL and what we call streams, which gives you more information about the metadata of various changes and also the data lineage of the current state of the database. The data is replicated but deduplicated and can be read through regular CQL. Not just the pre-image, but also the deltas, and not just the post-image, but also the deltas and the pre-image. And you can consume all this data without knowing a whole bunch of distributed systems magic, which we know is not trivial. The core functionality is very simple, but it allows you to build more advanced things on top of it, which we will discuss more in the later part of the presentation. Next slide. The CDC log is partitioned into what we call streams. This divides the entire token ring space of the cluster, and each stream represents a slot in the token ring. This is the partition key of the CDC log table. The client reads the data in the CDC log table in a round-robin fashion and traverses through the token range. This is very useful because it allows the client to read the CDC log without doing any cross-node queries, which is a very expensive operation. It allows you to view a single partition group at a time and get a clear timeline view of the data. A lot of these details are abstracted out if you are simply using the shard-aware client driver for these operations. So as long as you're using the shard-aware operator, most of these details won't even be visible to you. Also, we will roll out more functionality into our DynamoDB compatible API, aka alternator. CDC will be the basis for alternator streams. Let's go to the next slide. Now, just to recap, CDC in Scylla is very easy to integrate and consume from your application, as it is available via CQL. It is a robust system and provides the same consistency guarantees as your base table. There is some reasonable overhead once you turn this feature on, even though the writes and reads are grouped efficiently to the replica ranges. So provide the system with sufficient resources once you turn on the feature. As the CDC log data is TTL'd, we prevent any overflow if the consumer fails to act. I'm very excited to see all the applications and integrations you're going to be building using the CDC feature. And with that, I'll hand it over to Peter.
All right, thank you, Mahi. Hello again, everyone. I just want to take a moment for a quick audience poll. For a sense of scale, we'd like to understand how much data do you have under management in your own transactional database system? Less than a terabyte? 1 to 50 terabytes, 50 to 100 terabytes, or greater than 100 terabytes? Pick the answer that best matches your current data set. And I apologize, I went through the form poll very quickly, so we'll give you guys a few moments to answer this one. See, answers are coming through. Thank you very much. And thank you also. Remember to click on the Q&A button at the bottom to ask your questions. We'll get to those at the very end of this event. Okay, thank you. Now we'll close the poll. With that, now let's hear from Confluent's Tim Berglund on how to combine the capabilities of Scylla CDC with Kafka.
Hey, thanks, Peter. Let's go to the next slide. That says substantially the same thing. Anyway, I am Tim Berglund. Peter, you were very kind to introduce me earlier, and I would like to talk in a little bit more detail about how Kafka works, because we've been talking about CDC and integration using Kafka, and it's been a little bit of a substrate to other architectural components in the discussion, which is a role that Kafka often finds itself in. But I think it's worth a little bit of time to just remind ourselves of the fundamentals and dig into Kafka Connect a little bit, which is the part of the Kafka ecosystem that enables enables CDC happening from a database, in this case Scylla, into Kafka. So next slide. As a to speak for a moment about Confluent, and I work in the developer relations team here at Confluent. We make an event streaming platform based on Apache Kafka, and it's our goal to create that platform and develop it and put it at the heart of every company. We believe that event-driven architecture is I would say a generational paradigm. This is a way that people are beginning to build systems, and probably 25 years from now, it will have become, the entrenched legacy way, and maybe in 25 years there'll be some new idea that's pushing it out of the way. But we view it as a real part of the future, and we do that again with an on-premise platform called Confluent Platform that builds on Apache Kafka, and also a fully managed service called famously Confluent Cloud. Confluent Cloud runs a hosted version of Kafka and Kafka Connect and KSQLDB for stream processing and a number of other features as well. Next slide. So Kafka is a log. So if you ever hear someone say Kafka queue, or if you think of Kafka as a queue, if you're a person who says Kafka queue, you should put a rubber band on your wrist and maybe snap it lightly every time you do to train yourself out of that habit. It's not really a queue, it's much more of a log. And as messages get written, you just saw some messages getting written into a partition log there in that animation. They stay there. Queues are usually ephemeral things, right? Where an event goes into the queue and then it's consumed and it's gone from the queue. Well, in Kafka, you have a configurable durability, a configurable retention period on each topic. So they really function as logs. And to scale, we split them into pieces, and we can distribute those pieces among multiple brokers in the cluster. And so topics can become really arbitrarily large. They can handle all kinds of events. We're talking today about CDC, but anything that one can conceive of as an event that one might want to store in an immutable and ordered way, that's data that can go into a log. Now, reading, it may be better to give than to receive, but it's a little more difficult to read than to write. So next slide, we'll look briefly at reading. We have that partitioned topic, right? This log that's broken up into pieces, and I can deploy a thing called a consumer easily enough that reads from those partitions. And in this case, you can actually have multiple consumers. Again, if you think of a queue, which, as we've said, Kafka is not, a queue really, once you consume, the thing is gone, and implicitly you don't want anybody to be able to see it again. But a log, I can have one consumer read from that log and another consumer read from that log. Like I might have two separate applications, two separate concerns that are doing processing on that data, and I can stand those applications up, and they read from that log in orthogonal ways without influencing one another. And they'll get all the messages. Messages inside a partition are strictly ordered. Of course, between partitions, they're not strictly ordered because of, well, kind of because of the laws of logic. It just doesn't happen. So, by partitioning a topic, you lose global ordering, but that usually doesn't matter. Interestingly, usually just within a partition is what you want. And this is cool, but remember I said partitions could get really big. And so we might at times need to scale one. I might have more computation to do. I might want fault tolerance. I might just have a lot of messages because I'm doing CDC from some really high volume table in Scylla. And so next slide, we can see if I deploy additional instances of a given consumer, then the partitions get automatically reassigned to those instances. So reading is a horizontally scalable thing. Now there's a fairly long and detailed story to tell about how all that works in its particulars and where the gotchas are and so forth. But this is built into Kafka. Just by being a thing that reads from Kafka, I've got this horizontal scalability built into my application. So that's the basic structure of writing and reading. Next slide, we'll look at some other components in the ecosystem. And given today's discussion of change data capture, Kafka Connect is a key component. So this emerged, I think Kafka was about 5 years old in 2015. And what the community discovered is that people were doing data integration. They wanted to get things into Kafka from non-Kafka sources, and then they did processing of that data in real time in Kafka. And then they wanted to get it out to some non-Kafka sink out in the world. And those things exist. There are lots of reasons to have, say, a radically scalable NoSQL database like ScyllaDB in your life, or maybe you've got Salesforce.com, or you've got S3 or something like that. There are lots of reasons to integrate other systems with Kafka, and that's what Connect does. So in the middle there, you see I've got my Connect cluster, sort of indicated abstractly as a bunch of those rectangles. And Kafka Connect is a separate little distributed system that I stand up. I can have a single node, I could have 2, 3, 5, 10 nodes if there's a lot of work to do. But that's this other system that really behaves as a producer writing into Kafka and a consumer reading from Kafka. And we can deploy pluggable connectors into Kafka Connect to talk to source systems and sink systems. And there are literally hundreds of those. If you go look on GitHub, there are hundreds of them. Many of them open source and free, some of them free as in puppy, right? You take a puppy home and nobody charges you, but you have a lot of care and feeding to do. So that's potentially a thing, but we're really focused on one particular connector today that is a very well maintained and responsibly maintained connector. Free as we used to say, free as in beer, not free as in puppy. It's not that hard to use. Let's go to the next slide. And that's the Scylla connector. So there's a source and a sink connector. Again, source connectors get data in, sink connectors get data out. Next slide, and we'll look architecturally at how this works. It is built on a foundation of a project called Debezium. Now, if you know Kafka Connect and you ever talk to databases, you probably know what Debezium is. It's the foundation for most of the free and open source change data capture database connectors in the Kafka Connect world. And CDC is always a source concern, right? So syncing into a database is pretty easy. You just write records out. But reading from a database is kind of tough. And we just went through the amazing Scylla features that make this so easy to do in Connect. Some of the Debezium connectors for other databases, like there's work they have to do that is, we'll say, non-trivial. But being built on this foundation, the Scylla sync connector kind of participates in the broader ecosystem of Kafka source connectors in a very healthy way. Next slide. Here is the canonical architecture diagram for Kafka Connect, for the Scylla source connector. You've got the Scylla server in green, the base table, and then the CDC table, which we've just talked about how that works. And I don't, I hope as you were digesting the details of that, you didn't lose the forest for the trees, because the fact that Scylla does this is just really cool. Again, from a Connect standpoint, this is hard to do with a lot of databases. And when you dig into how each connector has to do this, there are just these vastly implementation dependent different edge cases and hard things. Well, Scylla just makes that table and says, here are the mutations, please read them in this trivial and partition friendly way. So that's really cool. You got the Scylla base table, it's creating its own CDC table. And so in the middle there, the Kafka Connect source connector, all it has to do is just read records from that table. That's the easiest kind of database read there is. And it does that. So that's a very cool thing. Then from there, that connector writes those records into one or more topics in the Kafka cluster. And that's a cool thing. So those topics, again, themselves can be partitioned. So that source connector and the Connect server may be handling partitioning and just kind of being a Kafka producer, and all those details work themselves out because of the functionality in those layers. Next slide. There's also the sync connector. So you might get data into Kafka. Maybe you want to run some KSQLDB queries on it, do some real-time stream processing on that data, and then write it back into Scylla for access by your applications. So that sync connector is going to consume from topics and then write those into the table. So syncing, of course, there's no change data capture to do on the sync side. You're just taking messages from topics. Where a new message shows up, well, you insert that row into the table in Scylla and nobody gets hurt. And again, there doesn't have to be processing in there. I may just literally read from one table and then sync, source from one cluster and sync into another. Or I may add value to those messages in between. Next slide. So here's that simple pipeline use case. So I've got some cluster, the big cluster over there on the left. I will CDC or source connect that into topics in my Confluent Cloud cluster or my local Kafka cluster. And then I can sync those into other clusters. Now, obviously, and we've covered this here today. If you know Scylla, it has a remarkable multi-region story. So you wouldn't use this for solving a multi-region connectivity problem. It's more, you want to think of this as a data integration tool. I've got a cluster here, and there are some tables in there that I have things happening, and I want them to happen in that different cluster over there also. And so you can use Kafka as that kind of integration pipeline. And it's not the nice thing about doing that is, you could write that code yourself. You know how to query from Scylla. But the nice thing about doing this with Kafka is you get all the scaling properties of Kafka Connect, the scale properties of Kafka itself, the durability of the log, and as always happens, when you've got a pipeline, it starts dumb, and then it realizes it needs to be smart. And so you need to start layering in stream processing in the middle. All those tools are available to you in Kafka. There are a number of ways to get that done, and it just becomes this native real-time processing platform to make your pipe a smart pipe instead of a dumb pipe. Next slide. Let's look at how this looks. So I'm going to create a key space here. That's just very basic key space called KS, then create a table. It's got a primary key and a couple of columns, and I'm enabling CDC, that magical Scylla feature where it just does all the work for me. And I don't even say thank you. It just does it. It asks for nothing in return. Next slide. I should say thank you to Scylla. So this is not intended for you to memorize, but I want you to have this, just get your eyes on this. This is the basic size of the configuration stuff you have to throw at the connector. So connectors are declarative. That's the whole point of Kafka Connect, is you're not writing the connector code. Somebody's done that for you. But you do have to configure it. So you deploy the connector and you throw some connection or some config at it. Normally in distributed mode, this would be a little piece of JSON, but this is a super easy way to read it. Fits on the slide nicely. You'd post that little piece of JSON to a REST endpoint. The connector would wake up and start doing its thing. Next slide. Now, then, of course, you'd want to insert some data. This is a radically scalable NoSQL database, so we're going to throw 2 rows at it. And we would throw those rows at it, insert those. Next slide. And then we get to look at what's happening in the CDC log, right? So you see the stream ID, a timestamp, sequence number, is it a delete, and then the actual the actual changes that happened. In this case, those insert mutations being captured in the CDC log. Of course, the connector is reading this directly, reading these rows directly. We don't ever need to see these rows because the connector queries them for us. What do we see? Next slide. We see JSON show up in our topic. In the config before, we had a JSON value converter configured, so it's turning it into JSON. We could make it protobuf, we could make it avro. You could make it comma separated values if you just want to watch the world burn. That's an option. But it is automatically now deposited in your topic as a JSON message describing the change that has happened. So you've got this change log built in Kafka with just about no effort at all. Next slide. Okay, so right now, this is just those deltas. So that's inserts, updates, and deletes. It's a CDC, a log-based CDC connector, so it captures deletes. In Scylla, if you recall, the CDC log will also give me the pre-image and the post-image, like what the row was before I mutated it and what it was after I mutated it. Just so I don't have to do all that computation myself on the delta. Current version, and when I say current, it's June 17th, 2021 is when I'm speaking. So if you're watching a recorded version of this, somewhere in the backlog in the next few months is for the connector to capture pre-image and post-image. So if you're using the connector, you don't see pre-image and post-image in your topic. You can't have them right now. But if you're watching this later in the summer, maybe in the fall, it may be that the connector will get those, because that's a supported feature inside Scylla. We just need to get that data out. And that's, or as the slide points out, that's already a thing Debezium has been over the before and after. Okay, next slide. If you want to know more, developer.confluent.io. We've got a lot of great content rolling out in the next month, again, relative to when I'm speaking right now. Great video course on Confluent Kafka Connect, intro to Kafka, a bunch of stream processing stuff, event-driven architecture material. So we really want to help you know more about how to use Kafka, how to use Confluent Cloud, how to think about event-first design, and that's all there. Next slide, and I believe we are back to Peter.
Indeed, indeed. And I want to just thank all of our speakers today. It's just some fantastic content, and I know how much effort has gone into the preparation for this. So I just want to thank you guys for all your efforts today. It is now time to hear from you, our audience. Again, please use the Q&A button located at the bottom of your screen to ask your questions. We already have some questions that were asked during the presentation, so let's see what's already been queued up. The first one I have here, I think I'm going to field this to Mahi. This is from Celio. He said the CDC slide stated that partitioning of CDC log tables is the same as the base table. But he has a link to our documentation that suggests the partition key of a log table is something called a stream ID. What is a stream ID, and how does it relate to the partition key of the base table?
Yeah, so hey, can you see me?
Yeah, we can see you. We can hear you.
Yeah. So so when you create a CDC, so when you enable CDC on a table, that creates a CDC log table on the data, and there's the partition ID of that would be stream ID, the mutation ID, and the timestamp. So when you're querying or when you're looking for mutations, the data is co-located as the base table. So the base table mutation, the partition ID of a row of the base table is also a partition ID for the CDC log table. So they're both co-located. Imagine almost like a local secondary index. So you can query the data based on the partition ID and the mutation ID and the timestamp. So you will get a time sequence of all the events, all the deltas. So that would be the most fastest way to read the data, because there's a lot which is present in the data. So the payloads are heavy.
Right. Okay, and I think that this kind of also flows into the next question we had, which is, and in fact, let me see if I can answer this. You can correct me if I'm wrong here, but Goke asked, so does CDC not get written to the database? What does doesn't produce writes mean? And check me if I'm wrong here. So that when you do an operation, an update, write, things like that, it goes into the base table, and you do not have to do a separate operation. That CDC is basically like shadowing the main operation so long as you have CDC enabled on the table. Is that correct?
Yeah, yeah. So once you have CDC enabled on a table and you do your regular CQL-based statements, the data comes to the coordinator node, and the coordinator node checks, oh, is CDC enabled on this table? And if it is, then it's going to see, like, do you need the pre-image, do you need the post-image, or do you just need the delta? And then if you need a pre-image, then then it has to fetch the data. So there's going to be background reads that happen, and the data is going to be prefetched to the coordinator. And then whatever operation needs to be done will be done on it. And then the regular writes happen as it is. I'm assuming you're using the token-aware client. And then the regular RPC calls to the replicas happen, and then all this data is tagged along. So the writes are still the same, but the payloads start increasing a little bit.
Right. Awesome. Okay, so then I have another question here. Hi guys, this is from Bruno. Bruno is asking, hi guys, any recommendation to run all of those workloads in Kubernetes? I mean, some GitHub repos from Confluent would be nice, some examples. What do you have to say about Kubernetes and Confluent there, Tim?
Sounds like I should share a GitHub repo. We absolutely do have some of those, or some examples there, that are working purely with open source things. Also, Confluent Platform, the commercial thing, has, let me make sure I get the name right because we just came up with a new name. It's something like Confluent Private Cloud for Kubernetes, or it's an operator, right? It's a custom operator for Kubernetes to run, in particular, the Kafka and Confluent and Connect parts of the workload. And if you're super good at Kubernetes and you do things with storage volumes and stateful workloads, and you can do that, you can roll all that on your own. But it's nice to have something that's kind of custom fit around it. So yes, that happens. No, don't be afraid of it. Yes, you might want the commercial thing. Yes, there are open source things. I'll get you a link in a minute.
Great. Bruno also has a question about using Kafka secured with Kerberos.
That is, to my knowledge, a feature of the commercial platform, Confluent platform. And I don't think there is an open source way to do that, which is usually the story with Kerberos, right? Because it's named after an animal that guarded a part of the underworld for a reason. And it's difficult, and usually it's the thing companies want to do. So that always falls into the category of the commercial stuff. So confluent.io if you want to know more about that.
Right. Okay, let's see. The same for Scylla. So Mahi, do you want to talk about using us with Kubernetes?
Yeah, so we have a supported Kubernetes operator. So the Helm charts and the persist volumes and all these things are available on the open source piece. But if you want a fully integrated one, we have that available as well. And sure, if you're really good at this, we are hiring as well. So we're definitely expanding our team, and there are a very limited number of people who can do this efficiently, as Tim was suggesting.
So I also have a secret to reveal here. Version 1.3 of our Kubernetes operator was just released this morning. The release notes are now up, and keep an eye on our Twitter handle, because there will be a blog about the capabilities of using us with Kubernetes within the hour after following this presentation. Yeah. There is a question. This is a multi-part one. So the other one is, there are tools like Portworx to help us out when there's when there's some trickiness scheduling pods across availability zones. So is there any recommendation on the storage layer?
Yeah, I mean, I can speak a little bit to it, and um, if our Numberly folks also want to pitch in, that's fine. Um, so um, so you just have to make sure that your persistent volumes, whichever you're mounting onto these pods, they can move across, and sometimes they cannot because they're often sort of limited to a particular region. Uh, but yeah, so we work with Portworx as well. Actually, Scylla works with Portworx. So we are interoperable through their API. So feel free to engage with us, and we'll work through this a little bit more in detail.
Yeah, if I can share a bit of my understanding of current understanding of how and the work that has been done by the Scylla teams on this is we actually don't run Scylla on Kubernetes. We operate everything, the rest on Kubernetes, but not Scylla or Kafka. But what I think is interesting to challenge is how much do you expect this volume moving or staying available wherever your Scylla pod is scheduled to happen? How much do you think that it will fail and be moved over? Sometimes just a local attached volume is enough, even, and you don't have to care about this this data moving along. Why am I saying this? Because the Scylla devs have worked very hard, and there are very good talks in the Scylla summits in the time to bootstrap a new node.
Yeah.
So I think that in the case of Kubernetes, I wouldn't rely on yet another external layer in the stack to handle storage just before and to be rescheduled, etc. And just rely on the physics or on the insides of the technology itself, with replication factor and the high availability that Scylla brings on the table itself, and all the speed and optimization that has been done to bootstrap and to see a move on a Scylla cluster should be enough. And this is especially true with the upcoming work on the Raft implementation. I think that will help as well. So maybe you don't need it actually.
Yeah, I tend to agree, but at the same time, application development in generally, it's always a balance between how fast can we move and like scale it up, scale it down. But it's not the same trade-offs when you have for a stateful layer like a ScyllaDB or a database. The trade-offs are a little bit more rigid because you need to, as Alexis was referring, there's physics involved, and if you have to move your data across, that's going to take some copying of data or rsyncing the data, and a system like Scylla, you're pretty much limited by your disk I/O or how fast you can access your disks. And if you're using network-mounted disks or EBS volumes, that will become the bottleneck. So it's always a balance between that, the flexibility of scaling up, scaling down, and as you get for your application, I want the similar thing for my database, but also getting the maximum out of your database in terms of performance.
Great, thanks. Thanks for those perspectives. There's one last question here, and I think I can answer this one too. What are the differences between open source and commercial offering? Now, I know that there's a lot for the Confluent platform, but for the CDC connector for Scylla, I believe that's the same across open source and enterprise. Is that correct, Mahi?
Yes. Currently, CDC as a feature is available. All the feature set is available both for open source and enterprise.
Great. Okay, well, we're getting close to the top of the hour. So again, I just want to thank our speakers so very much. Thank you very much for attending our webinar. Again, we will make the slides available and the video will be available. Check out our Twitter feed later to find out more about what's going on with Kubernetes and Scylla. And again, thank you very much for attending. And remember to check out Scylla University Live, which will be coming up in a little bit. You can find links on our website to register for that. Take care, everybody.